from particle and photon sources, quantum effects in intense fields, relativistic laser-matter interaction, fusion research, high energy density physics, and a number of other areas as well. What they all have in common is they're enabled by some extraordinary laser designs and some extraordinarily high peak power pulses. He got his background over in Germany. He has spent time at Max Planck Institute for Quantum Optics, pioneering ion acceleration with ultra high intensity lasers. He also spent 10 years at Los Alamos. And so he's got a tremendous amount of experience and is very accomplished and really represents what is an amazing bridge between things that happen and go on at the Institute of Optics and things that are also going on at our laboratory for laser energetics. So we're looking forward to this talk.
Thank you, Tom. Thank you very much. And thanks for inviting me. It's a great honor to give the last talk of the season, I guess. Like most of my talk, it will probably go too long. I will try to be short, but usually I'm not successful. I will try not to be boring, and I tend to be better at that. So I want to talk about compact particle accelerators today and what they can do both in an applied sense and also for fundamental physics, if I get all the way to the end anyway. And I'll do that with two hats on. As Tom said, I'm leading a group for the last 10, 11 years at UT Austin now, where we use the text petawatt laser and some smaller lasers as well as some outside lasers to do that type of research. And about a year and a half ago, we founded a company, Tau Systems, now aiming to commercialize laser-driven particle accelerators because we think we and many other great colleagues in the field in the last few years have made the necessary breakthroughs that we are at a point where we can actually successfully do that. Okay, so why compact particle accelerators? I'm going to give a little bit of motivation there. Given that that's the colloquium, I'm not sure about everybody's background, but hopefully I'm not boring you too much with that. Laser plasma acceleration, how does that work? I'm going to talk a bit about free electron lasers, and because that is really our white whale out there. We want to build a laser-driven X-ray free electron laser. Not easy, but we think we can do it. And then I'm going to talk a little bit about strongfield quantum field theory and how we could test that with lasers. So as physicists and engineers and just maybe generally curious people, we aim for new understanding, and we need new understanding to solve the variety of problems our society sees itself faced with. And I'm very much a believer in a maybe little outmoded model of progress through technology. Maybe coming a little out of fashion, but I still think that's our best bet, because if as a species and as a society we prove one thing is we are not willing to sacrifice. So we better engineer our way out of that. And today we understand almost all the physical process in the universe except the extreme ones, or as it was put in one of my physics textbooks, Aristotle said a bunch of stuff that was wrong. Galileo and Newton fixed things up, and then Einstein broke everything again. Now we've basically got it all worked out, except for the small stuff, big stuff, hot stuff, cold stuff, fast stuff, heavy stuff, dark stuff, turbulence, and the concept of time. Other than that, really know how it works. We think, or a lot of the things we are concerned with, we find in what we call, or what we like to call, the ultraverse, and you can chalk that up to my new marketing people that I never had to deal with as a physics professor, but now as a CEO I have. Anyway, what is that? It's where things are ultra small, ultra fast, ultra powerful, ultra high pressure, ultra hot. Insert your own metrics there if you wish, but extreme conditions. And today we really can only explore these extreme conditions with gigantic particle accelerators, X-ray free electron lasers, synchrotrons, and again, depending on where in parameter space you go, very, very large lasers, football stadium sized lasers. Anyway, extremely big facilities, very rare and very costly. And what you see there is the Linda Queer light source and Berkeley's, or actually this is not Berkeley up there, this is Argonne, sorry, Berkeley is the lower one. Anyway, big campus-sized machines. And of course, if you go to fundamental physics, it gets even bigger, right? This is where we really still try to get at the very nature of how things work. This is the Large Hadron Collider in Geneva, and this is one of the plans for the future collider in Geneva, which is even quite a bit bigger and will probably never ever be built. It's already, I mean, even the planning phase is too expensive. So, but nevertheless, there's very good reasons that we want this, right? There is interesting stuff there to explore, so we want to do this. And how can we do this? So we want to replace the RF metal accelerator with a laser plasma accelerator, which makes it a lot shorter. It shrinks the accelerator from kilometers to centimeters. And that's a little disingenuous because, yes, the accelerator is centimeters. Literally, our accelerator cell that I show you later is exactly 10 centimeters long. Now, the laser, I will be ready to admit, of course, is still a little larger than that, and it's the size of a good room, which is still a lot smaller than this. And it's not just fundamental physics machines. This is the EUV lithography machine from ASML, and actually that's just literally the tip of the iceberg because there's a whole much bigger part of it underneath the floor, which drives it. That's just a stepper. So that's how you make the most modern, smallest size chips. And that thing costs, depending on its version, $150 to $350 million. So not a small machine. That's one of the EUV light sources you have. If you want to do semiconductor research, your other option is this, a synchrotron beam light. So neither one particularly accessible and or cheap. And there you go. However, very useful, right? Add a synchrotron. There's a lot of things you can do. And right now, I'm just thinking of semiconductor research, for example. You can get 3D images of compact designs. You can identify actually up there where the pointer here.
And there was a pointer there, yes.
No. That's okay. But that little yellow arrows, there's some defect, hard to see from the back there, but it's there. You can identify this. You can look at very tiny 3D structures, and not just that. I mean, this is semiconductors. This is more of a biology background. You can use the same technique, X-ray tomography, nano X-ray tomography, to look at biological samples, for example. So very versatile machines. That machine up there, by the way, is the Swiss light source, where they happen to have done those two experiments, so Paul Scherrer Institute. And if we can fit the big LCLS machine into a machine like that, maybe 20, 25 meters long. Now, the design we're working on right now doesn't go down quite to 10 keV like SCS does, but if we get down to 1 keV, 1 nanometer, I'm already pretty happy for a first try, but we think we can actually do that. And that would allow you to do, for example, single shot lithography, like at flash forward, or maskless interferometry. So there's a lot of applications already. And of course, it's water window, right? 4 nanometers to 2 nanometers, you're in the water window. Lots of biology you can do there. And it's a short pulse. It's a femtosecond or even sub-femtosecond X-ray pulse. So you can do these things that, well, that LCLS was built for. You can look at things that are destroyed by that high X-ray power, but you can look at it so fast that you get the image before you destroy it. And that's a very powerful technique because it allows you, especially when you think of biological samples of proteins or things, it allows you to look at things that you can't look otherwise. Because if you want to look at it at a synchrotron, it doesn't stay still. You have to crystallize it, you have to freeze it. And for most proteins, that just doesn't work. I mean, you can freeze them, but you change their structure, so you're not looking at what you want to look at. With that technique, in principle, you can look at the whole bunch of proteins that we can't look right now. We have looked at about 200,000 proteins, got the structure with crystallography at a synchrotron and with cryo-EM. This is a new technique. We haven't gotten about 200,000 proteins out of 200 million. So there's quite a few to look at yet. X-ray induced acoustic computed tomography is something we work with colleagues at UC Irvine, which is very interesting, actually. It doesn't actually need a full FEL. It just needs something like a synchrotron beam. It needs an X-ray pulse, and the key is the X-ray pulse needs to be short, because what happens is you have one short X-ray pulse that hits a sample, and what it will do is it will launch a shock wave. It will launch a sound wave. And so if you surround that sample with transducers, and you can basically get an ultrasound image from one X-ray shot, and you can basically get a three-dimensional image with one or at least very few X-ray shots. And if you compare that, you can, for the right samples, you can get images that are every bit as good as a tomography, as a computer, as a CT. And the CT, of course, you do that by taking many X-ray shots. So you get exposed to quite a bit of radiation, which, if you want to do it on a regular basis every other year, say, is not what you want. And this is something that we could probably do with a rather compact laser. You don't need the FEL, you just need the Betatron radiation coming out of the acceleration process, as I'll show you in a minute. You increase the laser energy a little bit, and you can use that same laser to do very high electron energy flash therapy, radiation therapy. You're still using electrons like in conventional radiation therapy, but where conventional radiation therapy, you have about 6 MeV. Now you use what for medical people is very high energy, which is about 200 MeV. If you want to, this is being explored by a consortium from CERN and a hospital in Lucerne. Clinical trials, this works, this is promising, but it needs a big accelerator. They're actually proposing to use one of the CLIC modules, compact linear collider modules. This is a superconducting linear accelerator module, which is definitely complicated. And whereas 200 MeV might be high energy for the medical community, it is actually very low energy for laser plasma acceleration. So again, a fairly compact laser, if we can get it stable enough and if we can get the repetition rate high enough, could drive this. And okay, so in laser plasma acceleration, for a long time, the community milestone has been, we want 10 GeV electron energy from a single stage. Now, I just told you that there's a lot we can do with 200 MeV, and that's true. But for a lot of things, 10 GeV is kind of the magic number. It's been defined in this report here and been repeated in many other ones since. And we want 10 GeV, and we want about 100 picocoulomb charge per pulse. And why do we want that? Or why was it defined in that report that way? Because with 10 GeV, you could now actually drive an X-ray-free, a hard X-ray-free electron laser, like LCLS, right? LCLS uses about 15 GeV. So depending on how you build the undulator and depending on what energy you really want, 10 GeV kind of is the magic number will do it. Also 10 GeV in a single stage is sort of large enough that you can dream about building a future collider. If you have a 10 GeV stage and you take 100 of those, bless you, you get a TeV, right? You collide that, you have 2 TeV center mass energy. So all the collider dreams of doing a laser-based electron-electron collider, lepton collider, again, 10 GeV, I mean, better, more would be better, but at least 10 GeV, otherwise you just have too many stages. Now, the kicker here, of course, is to get any type of luminosity that is of interest to a particle physicist, you need to run this also at about 15 kilohertz. And since every stage is driven by a petawatt laser, it's a challenge. I don't think we're going to see it tomorrow, but we'll be working on it. So for all the laser builders, they are 15 kilohertz petawatt lasers. So that's definitely something we are working on. Now, the lasers we're talking about are all enabled by something that was invented here in Rochester by Gerard, Mourou, and Donna Strickland, called chirped pulse amplification. And the idea is you stretch a pulse, you amplify it, and then you compress it again. And it's a little better graphic there. So you have a short pulse, you start with a short pulse. You can't amplify it straight away because if the pulse is very short, the power levels get high very fast and you damage your optics. And also you don't want to go through any transmissive material because you introduce B integral and you damage your pulse as well. So what you do is you stretch it by sending it through a double pair of gratings, arranging it such that in this case, the blue, if you look at the upper part there, the blue light ray, because it's a short pulse, right, it has spectrum. It's not your typical laser beam, it has spectrum. So the blue part of the spectrum has a longer path length than the red one. So it will pull apart in time. The red one comes first, and then the blue. Now you amplify it. As you amplify it, you also increase the beam diameter to keep the fluence constant and not damage your optics. And then you do the opposite, you compress it again, and you end up with now an amplified short pulse. Once you've done that, you can't go through any material anymore, including air. From here on out, everything's in vacuum. And everything is mirrors, no lenses. And if you do this right, you can actually produce very, very, very high intensities. This is Ganesh, one of my grad students, is actually now a postdoc at Argonne. Did this in his PhD thesis. We took the Texas petawatt laser, which is in this case, full energy shot was about 105 joule, 143 femtoseconds, and using an F1 parabola and adaptive optics, a deformable mirror, and a lot of very painstaking optimization, because unfortunately the petawatt laser is a glass laser that only shoots once every 2 hours or so. So optimizing that took a while. Nevertheless, he managed to basically get it to focus down to a tiny spot of about 1.8 by 1.5 micron and reach intensities exceeding 10 to the 22 watts per square centimeter. So those are very, very high intensities. And then we did a similar experiment at the 4 petawatt laser in Korea. We reached about 5, 10 to the 22, and actually they've been keeping at it. Wasn't involved in these latest experiments, but they are saying now they reach 10 to the 23 watts per square centimeter. So what does that mean? Well, we look at intensity here in watts per square centimeter on the lower axis, and then field strength, electric field volt per meter on the upper axis. We can identify a few interesting points. So here at about 10 to the 18 watts per square centimeter for a 1 micron pulse, so 800 nanometer pulse, the A0, the dimensionless light amplitude, is equal 1, which means that the electron will gain its rest mass in a half cycle of the laser pulse. So from here on out, we have relativistic optics, basically. All the electrons immediately get relativistic, and more so as we increase the intensity. Now, one thing that we've always been dreaming about, because we can do so many great things with laser accelerated electrons, and it just doesn't work the same way for laser accelerated ions or protons, because the protons are very far still from getting relativistic in the laser cycle. We can only accelerate protons or heavy ions by setting up plasma fields with the electrons that then accelerate the protons. A lot less efficient. But to get the protons relativistic, we would need to be at about 5 times 10 to the 24 watts per square centimeter. And if we keep increasing that at about 10 to the 29 watts per square centimeter, an electric field of about 10 to the 18 volts per meter, we reach a critical field strength, or it's called the Schwinger limit, where the field is so strong that it basically breaks the vacuum, the quantum vacuum, and you can produce electron-positron pairs out of the quantum vacuum, right, from virtual particles. Now your potential in that field is basically an MeV, so you have enough energy there to create particles. And that, of course, would allow for quite a number of interesting experiments here. Now, as I said, we are not here, we are not even here. Right now, we're about here. But there's a trick to get up there, which I will come to in a bit. First, though, let's look at how are we accelerating electrons. I want to now go and talk about electron acceleration, and this is somehow, hoping that's not happening to all the movies. This is somehow stalled here. Zoom, okay. I think it's the Zoom connection, but either way, so what we have is, right, I can talk through this. We have a gas cell. We have a gas cell where we fill it with helium or hydrogen, and we send in the strong laser pulse, and we're really at this low end of the strong spectrum, about a few times 10 to the 18, maybe 10 to the 19 watts per square centimeter. We send this in. Let me see if I can. And the laser pulse will ionize the gas, will ionize the electrons, and it will push them out sideways. Doing that, it will basically create a wave. It will create a wave behind it. It displaces the charge, so there is a plasma wave running behind the laser pulse, and electrons can run sort of on the outside of this bubble, right? And they can, at the end, there's they can be funneled and they can be injected into this bubble where there's a big charge separation field, and as long as they are in the right part of the bubble, they see an accelerating field or trailing behind the laser pulse. They get accelerated, and they can. The space charge fields are basically order of magnitude the size of the laser field, so we can reach very, very, very high fields, gigavolt per centimeter type fields, actually. And that is what makes plasma accelerators, laser plasma accelerators possible. We can create much stronger fields that you can create with radio waves. And B, since it's happening in a plasma, right, even if you can create those with radio waves, in a metal structure, you couldn't support them, you would damage your metal. The plasma is already, you can't damage it anymore. I mean, it's about as damage as you can do. So that's basically right, what we have here. We have a laser-driven wake field, right? You have the laser pulse. You have the laser pulse up front. It displaces the electrons. You have this charge separation field. And if you trap electrons here at the right place, they sort of run down this potential and get accelerated. Well, until they catch up with the laser pulse, because the laser pulse runs in a medium, so it doesn't run with the full speed of light. And so at some point, they will catch up. And then they will not be accelerated anymore. And that's what we call dephasing. That's one of the limitations here. But anyway, this has been done by many groups. This is the one from Texas that for a while in 2012 or so was the record for plasma acceleration 2 GeV with this 150 joule pulse using this method, basically. And said other groups, the group in the US that's been working on this even longer is the Bella group at Berkeley. they actually demonstrated the first 1 GeV beam, and then continuously increased the energy, 4 GeV, 6 GeV, 8 GeV, using a little shorter pulse laser with less energy than it takes us. They got the energy up, but they used a very, very complicated experimental setup where you had multiple laser beams to heat the plasma, to create a channel, to form this, and then to basically drive it. So it's a rather complicated experiment. They got up to 8 GeV, so pretty close to the 10 where we really want to be. But the problem is there's almost no charge left with this method. It's only 5 picocoulomb. We want 100. And my group did some experiments in Korea at the 4 petawatt laser. So now the lasers get bigger. We got up to about 4 GeV, maybe 4.5. Little more charge, some tens of picocoulomb, but getting there better, but really then just hit a wall, even though the laser was nominally 4 petawatt. And many, many other groups around the world, don't want to show all of that, but pretty much the same thing. It just didn't break through. We didn't get there. And well, we thought, okay, what can we do? Besides laser-driven wakefield acceleration, you can also use particles to drive a wakefield. You can use beam-driven wakefield acceleration. There's an experiment at SLAC, Facet, that has done that very impressively. And there's even an experiment at CERN where they use the proton beam from the LHC to drive a plasma wakefield. So in principle, you can do this. There's some advantages to that, but there's also some limitations there, right? The accelerators are huge. Without the electron bunch, longitudinal shaping, so your transformer ratio is limited to 2 for a symmetric particle bunch, and you can work through the math on that. The targets are much, much, much larger. You now have meter-long targets with very low density, many, many meters. And for the AWAKE project at CERN, the ultimate plasma cell is a few hundred meters long, actually, or supposed to be. It hasn't been built yet. But nevertheless, it's a good way. It overcomes some of the limitations of the laser-driven wakefield, for example, dephasing. And then there's something called direct laser acceleration, where the laser pulse can give energy to the electrons directly if you're at resonance. Problem with that one is the quality of the electron beam is usually not very good due to the strong Betatron oscillations. And the proposed schemes require additional lasers, alignment, synchronization issues. So not that easy, but nevertheless, these schemes exist. So we were thinking, well, it's my favorite French street sign, actually. Everybody's trying one thing, why not? Let's go for the other direction here and let's see, okay, can we get this all together? Right, everybody was just concentrating on one of the things. The laser groups were doing laser wakefield acceleration, Facet, and CERN, they were doing beam-driven acceleration, and really nobody was much trying with direct laser acceleration. So we said, okay, can we find a scheme where we can put this all together? And so what we have here is a simulation where we run a petawatt laser pulse in a plasma, and what you see is, as it starts, let's start. So you have the electron energy below, you have the intensity of the laser field in the middle, and then you have the XY phase space on top. And okay, you can see here, after about 4 centimeters, we're up to about 4 or 5 GeV as we were before, and then the laser starts dephasing. But if you arrange it right, what you can do now, here, you can see now we have the second peak growing here. We have the laser here starting to overlap with the peak of the electron bunch, can give it more energy by direct laser acceleration. And now, as the main laser is dephasing, the peak of the electron bunch can basically drive a beam-driven wakefield. And you see that this bubble is getting much larger than it would be just for a laser-driven wakefield. And keeping this going and doing this, we can reach basically 10 GeV in the simulation. Now, of course, it's a rather idealized simulation. lots of things. The resolution isn't there. It's only sort of quasi it's 2.5D really only. And so there's lots of issues with this simulation. But it showed us that in principle, this could work. So then the question is, okay, if this works, why doesn't nobody see this? Well, first of all, most of the experiments that have been done avoid reaching the phasing limit because you're losing energy again, right? And you're trying to get the highest energy. Second, the scheme is really available for a small range of plasma densities that are a little counterintuitive, and you may not operate there if that's not what you're trying. And in general, across the board, everybody observes a lot less charge in experiments than they observe in simulations. So we figured, okay, let's nevertheless try this, and let's use a gas cell that is longer than the dephasing length by design, and let's find out if we can increase the amount of charge and charge density. And we did this experiment on the Texas petawatt laser. I said 150 joule, 150 femtoseconds thereabouts. And this is the electron acceleration target area. So basically, laser comes from here, and actually, let me show you the setup. Well, this is the gas cell. Let me show you the gas cell first. So we designed a gas cell that's about 10 centimeters long, has a little metal plate on the bottom. And before we shoot the main laser, we shoot the secondary laser, but it's just a nanosecond yak laser, nothing particularly big. It ablates that metal plate, and it creates a cloud of nanoparticles. And then we let in the gas to fill the gas cell. And then it takes the nanoparticles with it, and so you have this cloud of nanoparticles distributed all through the gas now. And the idea is, okay, the laser, the main laser, the drive laser, will hit these nanoparticles. It will ionize them, and thereby create these large blobs of positive charge, which will, what they basically do is they influence the shape of the wake and can lead to capturing more charge in the wake, a lot more charge. And so this is the setup here. We have the gas cell, we have a laser, we have a dipole magnet, and two screens downstream from this. And when we did this, we indeed saw, well, not on every shot, that it's a single shot laser, so it took a few shots, but especially the first go around. But nevertheless, we got a very nice bunch at 10 GeV with about 340 picocoulombs. And we got many, many more shots that were almost up to 10 GeV, and almost all of them quite a bit higher than the 2 GeV we regularly got before, and quite a bit more charge as well. So here, basically, the gray area is where all the experiments from 2010 to 2021 had been with the petawatt, and then the red dots are what we're getting with the nanoparticles. As you can see, it's all over the place. The reproducibility is not very good, but given that the laser pulse reproducibility is not very good, that's not very surprising. So now, we'll go back. Now, the idea, as I said in the beginning, is, okay, we want to build a free electron laser with it. We want to drive a free electron laser. How do we, well, what is a free electron laser? So now, let's start this again here. So we have our electron bunch, send it through a number of beam focusing optics, but then you send it through an undulator, which is a alternating set of magnets, north pole, south pole, and so on. And so the bunch wiggles around, it undulates, which is why it's called an undulator. And as it does, it radiates, right? It emits synchrotron radiation. And the radiation field that it emits, together with the magnetic field of the undulator, and if your bunch has the right energy and other parameters, cause a feedback mechanism by which some of the electrons in the bunch gain a little bit of energy in the quantum-motive potential, and the others lose a little bit of energy, and so you get this micro-bunching at the undulator, at the wavelength, at your FEL lasing wavelength, basically. And once you get this micro-bunching, now your electrons are all in the right positions, and they can basically emit coherently. And you go from linear undulator radiation, where you just get whatever, so many photons per electron, you go into a coherent regime where you have an exponential increase in gain in the high gain regime, and you can get a really, really, really bright signal. So basically, that's basically just saying again what I just said. So to get the electron beam to lace, it must satisfy the Pellegrini criterion, and this means the beam brightness, how many electrons you have per spectral unit, has to be high enough, and for the ability to bunch the electron beam by the combined force exerted by the radiation field at the undulator. And when that happens, as I said, you get this micro bunching, there's your resonance condition there, and this is where the undulator will lace. And you have this undulator factor K here, which is a factor of the magnetic field strength, and the undulator period, which in typical systems we're dealing with here is a few centimeters, 2 centimeters or so, 3 centimeters. So question then is, can we generate electron beams like the LCLS XFEL? We need to meet this resonance condition. And LCLS, for example, has a very, very high emittance beam, and typically our laser beams are not that bright. The emittance is not that good, but there's a few things that we can do in principle to change that. The first thing is sort of the most straightforward one, kind of brute forcing it. We have this large energy spread electron bunch. We can send it through a chicane. We can filter it. And that works if the slice emittance of the beam is low, i.e. if for all intents and purposes, your electron bunch is chirped and you have all your different energies stacked up regularly. Then you can just say, okay, fine, I just take the part in the middle and I throw away the rest, basically. As long as that part in the middle is bright enough, it will lace. And of course, down the line, we would like to do this better and more efficient so we can improve injection. And there's all kinds of ideas, density modulated down ramps, nanoparticles, ionization injection, combinations thereof. We can try to increase the bubble size by using larger wavelength lasers. So there's a lot of things we can do, but the first thing to try is, well, can we filter the beam? And by the way, so at UT, we just sort of submitted a NSF STC center for 21st century X-ray sources. And Mike Downer is actually leading that, but Chen Joshi and Carl Schroeder from Berkeley, Chen Joshi from UCLA, of course, people from Michigan and so on. It's a big center to really try to make this work. First approach is, okay, can we get a magnetic undulator to lace? And then we'll see. I'll come back to that. But basically, here's the idea, right? The Texas petawatt beam, if you look at it, if you assume it has the right slice emittance, we could actually get this to lace. So the idea is, right, you have say this blob there, you don't even have to take the peak, take this blob at about 2.3 GeV, right? It has an RMS energy spread of about 2%, has about 800 picocoulombs, and about, you assume RMS bunch length, so about 40 femtoseconds. You can send this through a chicane, and you cut out the part in the middle that interests you. And if you do that, in theory, that indeed you would get it to lace with a 60-meter undulator at a power of 32 gigawatt at a wavelength in the water window, basically 2 to 4 nanometers. Tune it a little bit depending on where you put your electron energy. So in principle, this could work. Now, I wouldn't want to do that on the Texas petawatt because at one shot every 2 hours, that would be exceedingly painful. So we'd rather not do that. However, we could show that we can use the nanoparticle method on Ti-Sapphire systems, on smaller Ti-Sapphire systems. This was an experiment in Korea where you see no nanoparticles, beam gets a lot smaller there, and also transverse divergence gets a lot smaller there. Unfortunately, with the small laser, we lose a lot of charge here. We still need to understand that. But luckily, with larger lasers, this becomes less of a problem. We did an experiment at the Center for Advanced Laser Acceleration in Munich, where it is a few hundred terawatt system, 500 terawatt or so. And we just did this. We're still analyzing the data, but the interesting part is that tiny little dot here, because that's at about 2.5 GeV, and it is a very, very narrow energy spread, and there is enough charge in there. That's 100 picocoulomb. So that should work in principle, and that's a laser that fires once every 10 seconds, so that's a lot better to work with. So we'll see. Still has some issues with optics and stability, but we think we can get there. Also, that means if it works there, the petawatt laser at Bella, which works at 1 hertz, should also be able to do this, basically. So this is all looking pretty good. And of course, we are not the only ones thinking about this. The first ones to actually demonstrate that this could work was a group at SIOM in Shanghai. And they had a few hundred terawatt system, 300 terawatt system or so, and demonstrated FEL lasing at 27 nanometers. And then the group at Dresden, together with French collaborators, also with a sort of 100 terawatt system, demonstrated lasing at 267 nanometers. And they also, since that is conveniently the third harmonic of the Ti-Sapphire laser, had a very easy way to seed this. So they seeded this with the third harmonic and could actually go from the rather broad, very chaotic pulse that you get from a SASI FEL to a rather nice bunch if you seed it. So very, very encouraging. The big thing to work on, none of these FELs are saturated. Nobody reached saturation yet. So that's what we're trying to do right now. And we are working together with the group in Berkeley there, which has built a very nice system, a 100 terawatt system to drive an undulator, the old VISA undulator from Brookhaven. And they got a very nice grant from the Moore Foundation, $10 million or so to build this. And they spent a few years and built this. And now it's sitting there and it's beautiful and finished. And the Department of Energy, in its infinite wisdom, has basically said, yeah, we don't care. We're not funding you. So as they are a national lab, if you don't have a charge code, you're not working on it. Luckily for them and for us in this case, we are interested in that. And so we said, as the company, we said, okay, fine, we'll fund you. So we've been working on this together for the last half year or so and have actually been able to make quite a bit of progress. This is the beamline there, gas target, focusing quadrupole to chicane, more beam steering quadrupole, spectrometers, the undulator. It's a very nice undulator that actually has focusing built into the undulator, so we can really try to steer the beam through there. And then, of course, spectrometers down the line. And first thing we did is we actually stabilized the beam quite a bit. We put in active beam stabilization into the laser system and closed loop feedback mechanisms. And we can get now a very, very stable, for laser accelerator anyways, pulse at about 100 MeV. 100 MeV is not where we ultimately want to be with that system, but it's a good start at 100 MeV because it makes for easy experiments. Given the undulator parameters, at 100 MeV, that system will laser at about 400 nanometers, which is easy to see. And there's a lot of cameras that we can insert in the undulator at various positions and screens for the electron beam. Can't really say much about this yet, but this is just a series of shots at 1 hertz, and every now and again you see it really flashing. But this is undulator radiation, no doubt about that. And every now and then it flashes really, really bright. So that's very promising, and that's all I'm going to say to that today. So now, I don't know who knows Asterix here. It's a very famous European comic, and of course the Druids are near to my heart. They are the closest, I think, that they have there to a scientist, and of course they are very famous for brewing their magic potions in a big cauldron. And they also have a conference. They go to conferences. So they have the conference once a year in the forest there, where they show each other what they've developed and try to give out a prize for the best druid. And so we have this guy here. I really like this guy. So he says, look, I've invented a method of making powdered soup so it can be carried around in little packets. much less bother than the cauldron. And right he is. But the chair has an objection. It says, yes, but to make it into soup, you still need a cauldron, right? So he says, yes, well, I thought of this, our chief druid, and invented a way to make the cauldron into powder too. Why am I telling you this? Well, just showed you that we have a way to replace the generator with a laser. And we replace the undulator with a laser as well. I think we can, and more importantly, I think Chen Joshi thinks we can. This is his idea, actually, or grad students. And the idea here would be, and this is part of what we're working on with this new center, the idea is if you can micro-bunch the electron pulse that you get out of the laser plasma accelerator on a nanometer scale, i.e. on the scale of your emitting wavelength, you can now collide that electron pulse with a second laser of the right parameters, and that second laser will now be your optical undulator. So now you've really shrunk the whole thing down to a very, very small size, if that works. And there's some simulations that Chan's grad students, let's see, Xu here has done and published. And if you can do this with a sort of 100 MeV class beam, so a lot less than the few G beam we've been talking about, you can figure out how to really use a modulated ramp down density gradient to micro-bunch this before it comes out of the plasma. You can then indeed create sort of 3-4 nanometer very bright radiation. So this is the bunched case, this is the unbunched case. So that's a very, very exciting concept, and it would be very, very interesting to try this out. Only right now there is no system that can try this out. So that's definitely something we would like to work on in the future and see, can we show this somewhere? All right, okay, so the end, coming towards the end here. I know I'm talking in the Institute of Optics, but I'm a physicist by training, so I have to put a little bit of physics in here. And what can we do in terms of fundamental physics with these amazing lasers? And one of the things is we can look for quantum processes in strong relativistic fields. And why would we do this? Because, well, they are very ubiquitous in numerous science frontiers. Gravity, for one, we don't have a quantum gravity. We don't have the theory of quantum gravity. But if we ever want to get them all together, we need one. And particle creation in black holes, of course, is a problem, an example where this would matter. Emission from pulsars, magnetars. In QCD, the Barton distribution function, hadronization, and quark-gluon plasma formation and thermalization is actually a strong field problem that is not very well understood. And in QED, we have radiation reactions. So how does an electron emit radiation when you have to take into account the field it's emitting itself acting back on it, which happens, but it only matters when the field is very strong. Vacuum polarization, spontaneous vacuum pair creation, as I said, when we reach the Springer limit, can we control the quantum vacuum as an optical medium? There's been some great experiments proposed and things calculated. Can we actually do this? Well, that would be very exciting to find out. QCD and general relativity do not really provide ready laboratories to test these in controlled experiments, right? Because for general relativity, well, you can't really reach the black holes that are out there, and the quark-gluon plasma, we can create it, but it's hard to see the details. Now, ultra-high intensity lasers, on the other hand, could potentially provide a platform to develop and test strong field quantum field theories in the context of QED, And if you have something that works and is tested and we can verify it, we can think about these methods that we use to make it work and maybe apply these to other fields as well. Maybe, actually, let me skip this one because I'm running out of time. Maybe we can even look for something directly. And something that's very interesting to think about is the equivalence principle, where you have gravitational mass on the one side and inertial mass on the other side, right? And of course, we assume that's the same thing, right? That's what we teach everybody in mechanics. And it's a postulate. And so far, it's been true. But at a quantum level. So there is something called Hawking radiation, which happens at the event horizon of a black hole, where you can have radiation emitting from that event horizon, basically, and Angelina is going to hate me for that, but by creating a virtual pair of particles, one of which falls into the black hole and the other stays out. Simplified, but all right. Now, in principle, as suggested by Mourou, if these things are the same, if you accelerate something fast enough and violent enough, then you also create an event horizon where exactly the same thing should happen. And depending on your parameters, you should be able to detect a thermal radiation associated with that phenomenon. And so there are some papers out there that prove exact equivalence and computation of a radiation observable, right, by Bell and Lenas and Pena and so on. But there's other papers out there that claim an observable signature that's different from the standard radiation physics. They're all out there. They have not been tested. If you could test those, that would be actually very, very exciting, because if A is true, and you can get to a point where you can actually measure quantum gravity effects, well, now you have a laboratory to work on quantum gravity. And if it's not true, well, that's potentially even more exciting, because you just proven the equivalence principle is wrong. So that's a very interesting thing to consider and to go after. And a laser accelerator could be a tool to do this, because you can keep very, very high acceleration for rather long distances, and it might just be sort of the perfect point in optimization space to really measure something. And before you get there, actually, before you even have to worry about this, if you take your laser and you collide it with an electron beam, and of course you could do this at a big collider, but no big accelerator is set up for that. But if you do this, you will actually now, you collide a very intense laser like the ones that I showed you with a very high energy electron beam, you will now, in the frame of the electron beam, have a very much higher field, relativistically boosted field, where you can actually exceed the critical field, and you can first start to work out your strong field QED. You basically now have to do non-perturbative QED. And again, there's many people doing this, but nobody being able to validate it. So which of the many models work? We don't know. And you would have to get that one right first, because any gravity signature would be a lot weaker than that, and that's already weak. But that's a engineering problem. So one problem that my group wrestled with a little bit and we started working on is, okay, and this was in context actually here of the OPAL proposal. If you want to do these types of laser electron collision experiments, what's the best laser to do this with? Gives you the best chance to actually see something. And so we considered a big laser, 10 petawatt, 25 femtosecond pulse duration, 2 micron radius focal spot, 10 to the 23 watts per square centimeter peak intensity, and colliding with a 10 GeV electron beam at 1 shot per minute. Gives you a quantum parameter of 22. So that's well in excess of 1. So definitely reaches an interesting regime there. And then we compared that to a much more handable laser, much easier to build, much easier to run. 1 petawatt, 30 femtoseconds. Focus a little smaller, 1 micron, still very doable. 10 to the 21 watts per square centimeter, only 1 GeV electrons. Quantum parameter chi of about 0.5, but at 5 shots per second. And so the probability of radiation is proportional to the fine structure constant, right? And to chi, local acceleration, right? And so naively, the big laser achieves higher chi, so it should give you more events. However, the number of events, right, is proportional to the number of events per shot times the integral over your interaction and over the power levels there. And you do a naive estimate, you find out that actually your fast laser, even though it's a lot smaller, beats the big laser in terms of number of events by quite a bit. So one has to be really, really careful how to design an experiment like that, because it's very easy to go down the wrong path there. And of course, it depends on what you want to do. And this is very naive estimate. This is very 1D, very, right? But it's an optimization problem. Another thing we see, okay, what's your laser pulse shape actually? Depending on what your laser pulse shape is in time in this case, but the same, of course, applies in space. We looked at the sine squared, the Gaussian, sort of the 3-peak one where you have a pre-pulse and the seconds. And it really matters a lot for the exact same laser. Otherwise, you get very different chi that the electron that collides with it sees. Doesn't matter if the laser is making a larger field somewhere else in space. If the electron doesn't see it for the experiment, it doesn't matter. So that's something to consider as well, that there's many other parameters. There's a paper we're about to put out on that. And again, very interestingly, we defined the luminosity parameter for such a collider, and we compared the original Opal EP, the Opal 1. I think that one has evolved, so it's not quite what's currently proposed, but that was the original one. So we compared that with a smaller peak intensity laser, but with a rep rate of 5 hertz. So 100 times smaller peak intensity, but 300 times higher rep rate. And it consistently does better at pretty much all the colliding energies. So you got to be really, really, and then this is something, of course, that particle physicists know about and do all the time. It's called phenomenology. You really have to calculate your detector through. In our laser field, we typically don't do that, but we got to. If you want to do these types of experiments, we got to do that. All right, and with that, just one slide for Outlook here. There is this wonderful old accelerator building on campus. Wouldn't it be fun to put such a high rep rate laser in there, maybe with an undulator or two? So that's something that we've been thinking about, and it could have a number of different end stations to do bio stuff, medical stuff, semiconductor stuff, or whatever else somebody has a great idea for. But that's basically something we've been talking about, and it would be a lot of fun, and I think would be very, very compelling to put that together, especially with working on very high rep rate lasers. And that's something we're working on that I didn't get a chance to talk about today, but we really would like to push beyond a few hertz. And even so we're right now in the company, we're putting together a Joule class system at 100 hertz as the next step. But where we really want to go is tens of kilohertz. How do we do this? Well, that's a real optics challenge. There's many, many different optics challenges in that problem, actually. And I mean, that would be a fantastic challenge for everybody to work on. And I think here would be a fantastic place with fantastic talent to try to figure that one out. So with that, we give you a few slides about the company very shortly, just because people have been asking. And so we're headquartered in Austin, right downtown, very nice location. We have made some agreements with UT that allows us to use the labs there. UT had a hard time putting that all together because we're a physics department. We're not used to dealing with companies, but after a year, we figured it out. So now we can use the labs and they can get some funding and we can modernize the labs and everybody's happy and everybody benefits. And We're up to some 20 people right now. There's some faces you may recognize that are helping us down here. And it's been one hell of a ride. We've been growing fast. This is actually already outdated again. We have teams on the experiments, of course, but on theory, on engineering, on data science. We have our collaboration with Berkeley. So things are really going pretty fast. And again, I think here, there's a lot of talent here in Rochester that we would like to bring on board with that and to work with. And so with that, thank you very much for coming. Oh, I only overstepped by 5 minutes. Thank you.
Question. You have time for a few questions? Well, you're thinking, oh, go ahead, please.
Right. So one of the things that you're very much well aware is that Wakefield acceleration has been working on this problem, stability of divergence, et cetera, brightness for a very long time, for 20 years basically. So this new scheme that you proposed seems like it has its own challenges with that. Could you speak a little bit more to this problem?
Oh, absolutely, absolutely. And so it's one of the new schemes we're working on. We're also like in Berkeley, for example, we are not using the nanoparticles yet. We're using just down ramp injection. There's many things that go into making the beams better, and many groups around the world have really made a lot of progress there. A large part for all the schemes is you will not get a stable beam if you don't have a stable laser, period. And if you look at a lot of the existing laser facilities, I'm sorry, you will not get a stable laser if you run it in a crappy building. So you really have to break it down from high to low. But on the other hand, there's a lot we can do, right? We added closed loop feedback controls to the system in Berkeley that has already helped. A big thing there, and this is the other reason why I'm pushing rep rate. As the rep rate increases, it is much easier to control things and keep it stable. At Berkeley, it's a 1 hertz laser, but it has a 1 kilohertz pilot beam that goes through, and that already helps. It's not the all and all, but it helps. So there's that. Now, to your other question, okay, what are the challenges of our scheme that we have there? Right now, the nanoparticles are wherever they are, right? We ablate them, and then we let the gas stream in, and the gas takes them with it, and it mixes it, and it distributes it. We assume somewhat homogeneous. We're now basically setting up systems to actually measure that, which, given that the nanoparticles are about 10 nanometers, is not that easy, but nevertheless, it's what we have to do. Adding probe pulses, high resolution, short pulse probe lines to the laser, to the axial interaction will help figure out what's going on. But we are working on a design where you would inject the nanoparticles at a specific spot at a specific time rather than all over the place. And that would definitely, I mean, as far as the simulations go, that would help. We'll see, the proof's always in the pudding at the end of the day.
Can you use transverse optical trapping to control where the nanoparticles go? And we do some of that here. But...
Well, yes, in principle, but the number of nanoparticles we are talking about is quite substantial, like billions. For now, but that's also a good question, because we're still trying to figure out how many actually participate at any given time and how many are important. At the beginning, we assumed, okay, the nanoparticles actually provide all these extra electrons that we're seeing. Now, with the simulations becoming a little more realistic, and they basically up the computing power quite a bit, and it seems that is not the case. What the nanoparticles seem to do, you ionize the nanoparticle, now you have a lot of positive charge sitting around, it changes the bubble fields in size. They breathe, and then they capture more particles on the outside of the bubble fields rather, and that gets injected. So very different optimization problems.
Since your focus is on the compact laser, compact design, I'm wondering whether you have any use for the omega laser, the LLE. laser lab? I mean, do you see any use of the omega laser for your work here at all? Or that's not useful?
Yes and no. I mean, there's of course many lasers at LLE. The one I'm right now very excited about is the Opal front end, which is an very short pulse OPCPA system, and if you can put that on the target, I think there's a lot of very exciting things one can do with that. There is a few things where even a large laser, I mean, ultimately, right, is this proposal to drive EP Opal, a short pulse but big laser. I mean, again, we just have to figure out what's the best thing, the best sort of design compromise for that and for what you want to do with it. But that is super exciting. But then also you can flip it around. We are making very bright X-ray sources. That actually should be very interesting for the people at Omega that want to look at their fusion capsules. So, and we've been talking to other fusion groups. I mean, there's a lot in diagnostics there that can be done, basically.
Just heard it. I don't know much about all this, but so what's the, so you said you want a 10 GeV from one stage, right?
Right.
And the 10 GeV, does it correspond to the energy of this electron bunch?
Yes. So from our, okay, so actually I should have, a very good point. Should I come back to this? Yes, with the Texas petawatt laser in our experiment, we got 10 GeV from one 10 centimeter long gas stage. So we got 340 picocoulombs in a 10 GeV bunch, in a very narrow 10 GeV bunch. So yes.
So how does that energy affect the X-rays coming out of your FEL? So
well, okay, so that particular laser is not driving an FEL right now, right? But if it could, right? And as I said, the big problem with that particular laser is it only shoots once every 2 hours, right? If we could build that laser with rep rate or something that has sort of similar parameters that we are now understanding, yes, with 10 GeV, we could actually build a hard X-ray FEL, so 10 keV, 15 keV X-rays. So that would really be the same regime as LCLS, and therefore could do a large part of the experiments that LCLS could do. I mean, of course, they are now building LCLS2, which is at a megahertz, which is, I mean, I'm not saying we're going to replace LCLS, right? I mean, this is more like, if you think back, computers used to be building size things, and now they are this. Well, we still have building size computers, and we still build new building size computers, and they can do a lot of things that this here cannot do, even though this can do a lot more than the first building size computer. And then that's how I think about it. There's always going to be a place for LCLS at the other big accelerators, because that's the forefront, and they got 2,000 people working on it. I mean, that's very different.
Any other questions?
Online question, Tom?
Yeah, go ahead, Wayne.
Hey, so thank you so much. I think that's really a visionary talk, and it's really exciting. I can't help but think about, Gerard, when you talk about this stuff. And I think that Gerard Mourou must be very happy with the kind of energy and the kind of vision that you have. It's fantastic. One thing I just wanted to say is I think that when you talk about the high average power, high peak power lasers like that, there are so many more applications. I mean, your applications are great, but I think everybody should realize there's many more important, many more applications for those kind of lasers. So that's a fantastic additional reason to do that kind of development. So I do have one question for you. At one point you were talking about, I think you were very excited at one point. You said that we haven't reached saturation yet. I think that was, you were talking about the FELs. And why did you say that? And what is the saturation mechanism? And why are you so excited about that? Does that mean you could just keep right on going, get much higher powers? Why did you say that? And what's the physics behind the saturation there?
Right. I mean, so you basically, it's your e-folding of the amplification, right? You have the gain length, and like in a laser, right? When you reach saturation, then your gain, you're at your limit. But that's what you can do, and that's what you should get, right? You would get a lot more power than what has been demonstrated so far, and so that's what we want to demonstrate. We want to of course build an FEL that reaches saturation on every shot, and the way to do this, I mean, the brute force way to do this is to build it longer and longer, but of course we also want to build it compact. So you really want to keep your beam nice, and you want to keep refocusing it, and you may want to have a tapering undulator to sort of keep the beam matched to the undulator parameters. So, what it basically means is you need better beam quality to reach saturation faster. And so that's where the research is that we're working on right now. But if we manage this, then the FEL will be very, very, very much brighter, right? You basically, your gain grows exponentially until you reach saturation. And so that's...
You're just thinking the saturation is due to depletion, or is it due to some other nasty physics?
Well, yeah, at some point, you basically just kick your electrons out of the resonance condition.
Okay.
Basically.
Okay, thank you.
And you lose too much energy. When the electrons, when they radiate, lose energy. Right. And by the way, thank you very much for your comment on the other applications. Yes, there are many applications. Even just for the lasers, the high average power lasers, forget any particle accelerators. There's so much stuff, but of course, there's only so many minutes in that hour that I get to talk here. So, but thank you. And anybody who has an idea for an application, please reach out to me. I'm very happy to talk about that always.
Okay, good. Thank you.
All right. Thank you very much. Oh, for optics students, there is one bonus talk remaining in the semester. Tomorrow afternoon, about 1:16, we're going to have a research seminar from another visitor. Stay tuned for that. It should be a really good talk.
It's not my you're available.
Either that or it's
That's sort of the strategy.
So, okay, good morning. That's what
Yeah, so I have, I got. Well, I could meet at 3, because I'm meeting with them at 3:30. Yeah. Yes.
I'm gonna go use. Right, and then on the way back out, the ride in Rochester, Chicago was made by 5 hours. So this can connect to Chicago. Let's stay in Chicago. This time around, yesterday, so my flight was at 2 yesterday, and at 9 I get an email from United. Oh, we canceled the flight. So we got right back there. So that and then you can stop. And then I rebooked the Southwest, but very
like where's a lot of power, but
that's where for Baltimore at like 6 in the morning.
I think the back of my mind.
And then drive to get them. Oh, okay, good.
Faculty are usually not
It'll work.
Well, I think it was like I think it's a great idea. It's like your number. You can jump in.
Oh, I know. Actually, I have no idea what mine is. It could be Ari Bodan, so 20 years. My wife, Andrea.
Vice versa. So the brightness of the X-rays is related to the charge of the right? Yeah.
That's right. Give the bond to like a David Doherty.
Yes.
Correct. I know that if you want to work to go there, and that's invited me to our. What happens? And I don't realize that I. With no box, it's just going to feel like what. But right you have a, well, I don't get the wrong number. No, I just have nobody calls me on my.
Right.
What happened?
Well, it will admit, but.
Wrong number.
Yeah.
You didn't give your name. I don't want to
Just,
hear.
it emits synchrotron, right? And you do the same thing as an electron bunch, long electron bunch just running around in the circle. Constantly, it's the same mechanism, right? But exactly.
Of course, autofill
And here it do, I get emails, just drive instability. Basically.
Yeah, and you know.
Reason that it.
I don't think this one's for me. I didn't read it. Yeah.
But the radiation they emit superimposed with the magnetic field from the undulate. That is what gives you your overall field that causes the microwave. You need to arrange it in a very specific way, otherwise it doesn't do it.
Scientists, I was in Missouri.
Okay.
So I might be likely touches upon the high harmonic. Appreciate the advice you guys Indians.
Right.
Our lasers do the high harmonic generator. Right. So we're talking about. Yeah, see you tomorrow. Okay.
Oh, are you going back to the lab?
I'm going back to the lab.
Right. See you tomorrow. Okay, yeah, all right, perfect. Report. So I talked in over the.
Okay. Raul working, but I couldn't find my swells. Actually, he's got shots tomorrow.
So I hadn't seen my view of.
Yeah, do you want to connect with them now, just here? Or?
Yeah, I think we can, I mean, I'll leave it up to him. If he wants to go back, you can go and. We're not allowed to relax around.
He's interviewing.
Come on. Gotta put him through the radio side. You can.
Got to get that much. That's what we do at LA anyway.
There are some areas on that yellow and chip. It's not unlike what that was. So there. Look at it. You need that. It's you need to get the. You need to match it basically. You need to match it all under, but yeah, it's you need. All right, yeah, absolutely. No, I'm gonna look at one of. And when it's one of the reference, the speeds for very high repetition.
I think it was Campbell's work, the extra laser is a little more
fiber laser.
studied laser.
Fiber laser.